Hello, researchers. Once again, my name is Malcolm Shambana, and today we are looking at T and Z tests. Definitely, we are going to use Microsoft Excel. Remember, this is research methods, so we are not really going to the details of those respective formulas, the T and the Z test formulas, but we'll find a way of computing just from the data, then concluding whatever test results we are going to get from these two tests using Excel. Thank you. So sit back, relax, enjoy your drink as usual, whatever you like doing as you are watching this session. Thank you. So, like I said, my name is Malcolm Shambana. You can reach me on +260 977 488 442. That's a Zambian number. You can reach me via WhatsApp, you can text me, or if you are able to call me, you can call me. Feel free. I also have a YouTube channel. I'm sure you are most likely watching on this channel. You need to subscribe to that channel so that you can easily be getting notification of any new publication from myself. And also, you can like the video so other or your colleagues may be able to see the videos. So today we are looking at several learning objectives. We are looking at the purpose of T and Z tests. That's the statistics, of course, quantitative statistics, and also looking at paired and independent tests. And thereafter, we go into performing tests in your Microsoft Excel. This will help you understand, or maybe help you interpret the data from your statistical recordings using these statistical formulas. You don't really need to know the inside of the formula or how the formula looks like, especially when you if you have time, you can look at how the formula looks at. But if you just have data and you know the purpose of your research, and you know what you want to achieve, the results, what you expect, maybe what you want to test, then you are better off using the same Excel, and then you just present your data in the Excel, then it gives you the results. Provided you understand the results, you are able to interpret what those results mean. Thank you. So we have the Z test and the T test. What you need to understand is when to use the Z test and the T test. Of course, the situations may differ. Though t-test is commonly used, I think due to limitation of data in the z-test. So I have this table where we are comparing the t-test to the z-test. The z-test usually has a normal distribution, and the t-test has a student distribution of data. The z-test, in the case of the z-test, the population variance is known. And in the case of t-test, the population variance is unknown. Z-test, the sample size is large, usually more than 40, or some say more than 30. Depends on your how accurate your results, how accurate you want your results to be, but usually it's more than 40. And whereas the t-test, the sample size is very small, it's less than 40 or less than 30. Depends on the requirements of where you are doing the research and your statistics. So usually these two tests are used to test if there is a significant difference between means of two categories or treatments. For example, you have boys or girls. If you want to test if the results from the boys and the results from the girls are the means are significantly different, or female employees and male employees For example, if their salaries are significant different, you would use the Z test or T test, depending on those conditions which we have highlighted there. If the population is small, you best use if the sample size is small, you best use the T test. And if you know the population variance, if the population variance is unknown, you better use the T test. But if the population variance is known, the Z test is used. And if the sample size is large, probably more than 40, the Z test is used. So in our categories, we are likely to have independent variables. For example, we can have provinces. You're comparing results from provinces between Lusaka and Southern Province, or you're just comparing the performance of boys and girls within a class. You have those two categories as your independent variables. And then the dependent variable is usually a numerical variable, which is most likely maybe being the exam score between the boys and the girls, or the salary scales between the females and males in an organization. You're trying to compare if there is any significant difference or they are almost the same statistically. So the two types of test under T test or Z test are the independent test, where you use two independent groups for your sample. You don't use the same group, you should use two independent groups for your sample to test results. In our case, we have boys, for example, boys, they're independent from girls, of course. Their scores are different. Not really different. You have got a different line of data scores for boys. You can also have different line for data score for girls. There is also paired test. You can use a paired test for Z test or T test on a same group by different conditions. For example, you weigh a group of people who want to, maybe they have been put on a particular diet, see if they are going to gain weight. You weigh them, say in January, and then later on you come and weigh them in the mid-year, say June. The same people. They've got different scales in January, scale reading in January, and different scales for scale reading for June. So you carry out that test on the same people, but under different conditions. Maybe after feeding them, then checking them after some time, after feeding them to a particular maybe diet. So pair test, independent test are both used in Z or T test. So we have an example of data here. I don't know how you have set your Microsoft Excel, but there are a few things you need to check. When we go to data, you need to have this on your far right of the screen called data analysis. If you don't have it, you need to go to your file and options. Then under options, you go to add-ins. So add-ins, you select analysis 2-pack. Once you pick that analysis 2-pack, you click on go, then it will upload and appear on the screen, on your screen, the way this one is showing here. So this one, why I use this one, it gives a lot of information upon just the input of data from my screen compared to using the usual formula. The usual formula, you have to do a lot of independent computation, but this one, just from this data, it will give you the mean, the standard deviation, and everything, whatever is applicable to that data. So I want to do a test score on on two groups, boys and girls. We are looking at their performance. These are test scores. So since there are two groups and two categories, the boys and girls, and then we have numerical data, which is these test scores about them, we can carry out a t-test. And provided the sample size, if this is a sample, it's less than 40, then the t-test is applicable. So in our case, if we want to know the t-test, if this we are definitely using a z-score, or we are using our standard error of 0.05 as the acceptable error. This implies that we're having a confidence in our data. We are allowing for confidence in our data at 95%. If you haven't gone through the hypothesis testing, please, you can find time, go through the videos. There is a video on hypothesis testing, and it will help you understand what we are currently doing here. So here, our expected error, we are giving a provision of error at 5%, at only 5%. So I'll go to my data. I want to carry out a t-test on this information on these test scores from a class of boys and girls, and we are trying to find out if there is a significant difference in the means between boys and girls on how they have scored. Is there any significant difference? That's what we need to find out. So I'll come here on it will give you quite a number of test tools, but we are only interested in the t-test. There are three types of t-tests in our case. There is one, the paired two-test sample for means. Then number two, we have the test. In this case, we are having a sample mean with equivariance, which means the variance for the girls, the data variance is equal to the data variance between the boys. In this case, you use the 2t. But usually we don't know the variance between these two. And usually, in most cases, it's different. So in our case, we are going to use the last one where we have a sample assuming that the variances are unequal. So we click on OK. Then we choose. It will give you the range where to choose. Then you choose the range where there is range 1, that's boys score. You enter, then there is range, the second range, that's the girl score. You enter, then it will also ask for hypothesized mean difference. And in our case, our mean difference, we are assuming that there is no difference between the mean score of boys and mean score of girls. So we leave it blank, implying that it's new. It's 0, no difference. So we have agreed that our alpha, our error, acceptable error is 0.05. So what we need to do next is just choose where to put the data. And here we say output range. Then we are choosing now the cell where our data is going to appear. So let me just pick the cell. So I would want my data to appear, say here. So I say enter. So my data is there. So the data which has come, it shows the mean for boys and mean for girls, variance for boys, variance for girls, the observed data sample size for each group, which is 9, 9 for boys, 9 for girls. The hypothesized mean is 0. The difference between the two means is 0. The degree of freedom, I think this one you may ignore it for the meantime, but it's usually computed by the sample, the total sample, which is we have 9 plus 9, which is 18, minus two set. We have two sets of data, which is 2. So now 18 minus 2 is 16. So you can ignore that unless in your spare time you can check how the degree of freedom is computed. Then we have the test statistic. Please, you can still refer to the hypothesis testing. I discussed this in the other session where we were discussing the hypothesis. Take your time, go through it. You find the video in the same YouTube channel you are watching. Then we have the the p value in the case where we have decided that it's a one-tail test. There is also directional testing. You need to understand that there is maybe one tail, you can have two tails, depending on how you have set your alternative hypothesis. Is it greater than or less than? If you have got a situation where you have got less than, greater than, then you have chosen a direction of your hypothesis. So in the case where we have a T one tail test, our p-value, according to what has been computed, is 0.147536. Then we also have our t, the critical value, which is determined from our agreed error, the 0.5. And it also considers the degree of freedom of which is 16. There are tables. We usually use tables when determining the critical value. But in this case, it has been computed for you through via Excel. So you don't need to use the table. So you have the critical value tail there in one test. So in this situation, where the test statistic is less than the critical value, which means that it's falling. This is in the case of one tail test, which means that the value of the test statistic value is below your critical value, which means it's falling in the fail to reject region. So the fail to reject region, in short, you are agreeing with the hypothesis. There is no difference between means. Between the mean score of girls, between the mean score of boys. That's the value which you have. Since this 1.08, let me highlight it, 1.08 is less than 1.74, then your test statistic is falling in the region of fail to reject the hypothesis. So you are, in short, you have just failed to reject the hypothesis, and you agree that there is no difference between the means for boys and girls. If this test statistic was higher than the critical value in a one-tail test, then we would have rejected the hypothesis. And also, if the p value, is greater than your error, standard error, the 0.05, your alpha, then you fail to reject your hypothesis. It's the same case as for the two-tailed two-tailed test. The 0.29 is greater than the 0.05. Also, the test statistic of 1.082 is less than the critical value of 2.19905. So that's the case. So we can conclude that there is no significant difference between the scores of boys and the scores of girls through the use of t-test. I also put in an example where I wish there would have been a significant difference. So I changed this, I maintained the scores for boys. I reduced the score for girls. Please don't take that as a gender discrimination. No, it's just an example, please. So I took a lower score for girls. If you want, we can switch. We'll switch. Let me switch. I'll put it here then. So we have a lower scores for boys and higher score for girls. So we test again if there is a significant difference between the means of the two genders. So we go back to our data, then we go to data analysis, then we say t-test. So I choose the data, I choose for boys, enter, then also choose for girls, enter. Our new hypothesis is that there is no difference, so it remains 0. Our alpha is 0.5. If you wanted, you would have had even 0.1, depending on your level, how you want how accurate you want your data to be. So I'll maintain the cell, so I go on OK. Sorry. Let me choose another cell. It was override. So I'll put it just next to this and say enter. So we have our new data there, where I've reduced the score for boys and almost maintaining the score for girls. So there is the mean for boys, mean for girls. There's variance for girls, variance for boys. There is observation, 9 observations. There is 16 degree of freedom. Then we have our T, which is now in minus. We have our T in minus 11.46387849. Then our critical value is 1.74, 1.74588836. So in our case, unlike the area case, we had the critical value higher. Just a minute. So one thing you need to note that is that for the for the t-test, we don't consider the minus, we get the absolute value. So remember our earlier case, we had our t-test was 1.08 and our critical value was 1.74. So we failed to reject because the t-test was less than the critical value. So in this new case where we have changed the results, we have actually made the results for the boys poor. We have our t-test being minus 11.46. You don't pick the minus, you don't consider the minus, you get the absolute value for that t-test. Please let me highlight it. So here we are looking at 11, ignore the minus. We are looking at 11.46 and we're also comparing it to our markup, your cutoff point, which is 1.74. This is usually derived from your error, the one which you have set up, which is 0.05, and it's compared to the degree of freedom for which is 16. Usually we used to use tables, but now, like I said earlier on, even in the earlier case, Excel has done that for you. It has checked the value for you in its inner table, I'm sure, I'm assuming, and we have found that our critical value, our cutoff point is 1 point. So 11 is higher than 1.74. So in this case, we reject the new hypothesis, implying that the mean score for boys is not significantly the same as the mean score for the girls. Also, the p-value are so low. If you can see, these have even been written in scientific form because they are close to zero. So in the case where we have a p-value lower than the setup alpha, which is 0.5, then we reject the new hypothesis and say we end up saying that there is a significant difference between mean score for boys and mean score for girls. So we move to the paired value, paired tests rather. So I have this data. Let me just clean up this one. Let me just create a new sheet for this. So for paired test, we have same participants, but under different condition and tested maybe at different times. I earlier on gave an example of, say, people have been put on diet. They want to see if this type of diet has a significant effect on the weight of those people. There is Mr. A, Mr. B, Mr. C, Mr. D, and so on. So initially, their weight is measured. Their weights are measured. That's so Mr. A was weighing 20 in January and 25 after being fed with good nutrition in June. He was weighing 25. Same as Mr. B, he was weighing 34. After being given good nutrition, he was weighing 37. Mr. C, 36. In June, 38, and so on. So this is a paired test. It's a test carried on the same sample, but at different times, maybe under different conditions. So we want to see if there is significant difference in the weight according to time and the given conditions. We go through the same formula. I go to data analysis. So remember there are three t-tests. There is a paired. There is a t-test where you know the variance, that they are equal variances, sorry. You might not know the population variance, but you know the sample variance, that it has equal variances, or you assume that the variances are unequal. So now, this time around, we are going on paired test because it's the same sample at being tested at different times. So I go on OK. I choose my range. So for January data, I enter. So for June data, enter. So we are assuming that there is no difference between their weight after January to June. That's our hypothesis. And then we say our error is 0. Our acceptable error, our alpha is 0.05, meaning that we have got 95% confidence interval in our test. And then I also choose where I'm going to put my data. So choose this point and then say OK. So we have our data there, we have our mean. So we have our means for variable 1 and variable 2. Then we have the variances for the two situations. This is, we can say, before and after. Then we have observations, which are 9. Then this time around, it even computes the correlation between the two sets of the data sets, between the one for January and the one for June. So there is a correlation of 0.97, which is quite high, which means there is a strong positive correlation in the same direction when they are correlated. So there is also the degree of freedom, which is 8. Then we have the t-test, which is minus 6.14. We have the p-value of 0, which is very small compared to the our 0.05, which is our acceptable error. And then in this case, we have our critical value of 1.85. The absolute value t-test is 6.4, which is very high compared to the critical value of 1.85. So in our case, we are rejecting the hypothesis that there are no differences. So in short, we are saying there are differences in means between January and June. Let me highlight it. There are differences between means in weight for these individuals between January and June. So whatever is being fed to them as nutrition or food or whatever they are testing on them is actually working. They're actually gaining weight. So this is how you do your t-test in your Excel. The z-test, it's the same, though there are those conditions where we need to have a sample larger than 30 or 40, and then it has to follow the normal distribution. But you still, if you have that data, you just come use the same route. Then you come and look for the z-test score. Then you follow the normal procedure. Then you will choose your data range, the variable 1, the variable 2. Then you choose your hypothesis. You put your variance for your the non-population variance. It has to be put in here for the two of them. If you don't have those, it's better you use t-test. T-test is actually commonly used in your academic research, thesis and dissertation. So please, you can like my video for any other updates. You can also subscribe to my YouTube channel. You'll be getting notification whenever I produce something. Hope you understood and enjoyed this session. And if you have any question or contribution, you can still post to my on my YouTube channel and I'll attend to that. Thank you very much. God bless you all.